Start the day. Whoops, not that. Let me see. Where did it go? There it goes. What did I say? 227? I think it was right before here. Oh, I just passed it. Jeez. Sorry about that. Should have had that ready to go. So this is the plot that I want to start with here. And so just be aware. You've probably figured out this little question right here is the simulation I was just showing in the background. This one. So if you want to check these, you know where that is. Jay, if you want, you could throw that in the chat. Just do a search for Moving Man, FET, and then throw that in the chat for them. I think this is a second copy I accidentally opened, so let me get rid of that. But yeah, so if you want to check things with the simulation, boy, that's pretty sweet. And so now we want to move down and do 2.27. And you can see that there's a picture of this graph here. And let me see if I can make this a little bit smaller. Let's go 150. All right. And so the idea is we're trying to answer this question right here and all of that it entails. All right. And so notice one of the first things you do in any graphing question. Let's say you have a quiz, say next Wednesday, perhaps. Remember, you should always look at the axis and find out what is on each axis. So based on this, you can tell this is a VT plot. Or you could even read this sentence, but it won't always be in there. So we know we're talking about a VT plot. Immediately, I think, I do not want to be using XT rules, right? So what I mean by that is, if you're looking at your notes, you say, okay, Jorsay gave us all these stupid notes. Here's the XT. Remember, if you don't identify this first, you're going to waste a lot of time and work really hard and get no points. So make sure if you're looking at a VT graph, you obey the VT graph rules. All right, let's see what's in the chat there. That's probably, oh, thanks. Appreciate it. And again, with that FET, I recommend doing the Java. Otherwise, it runs too slow. Even though Java has some security issues, I am confident in that. I've used it for 10 years, so that's going to work. All right, let's get back to it. And let's try and talk about these first few questions as a group. We haven't spent a lot of time on this, but so I'm most interested in seeing if you can look at the graph and think about these items before we get all this crap. So again, let's see if we can get parts A through D while the graph is on the screen. If you have trouble with these, it's because we haven't done them before. And so to remind you of another spot to look on this, remember, we also know this information right here. So this talks about the moving forward, speeding up, slowing down, all that stuff. One thing, I guess, if you really wanted to add something to your workbook, if A equals 0, what is true if A is equal to 0? Are you speeding up or slowing down? What do you think?
The acceleration is constant.
Constant. Well, acceleration is constant at 0, but what else is constant?
Velocity.
Velocity, yeah, good. Okay, and I think that's maybe what you meant, Erica. If so, that's cool. You got it. All right, so let's go back and look at this together. So maybe take a second. I'm not a big breakout group kind of guy, but maybe we'll try this just for fun to mix it up. Do I have that? No, let's not do that. I hate doing breakout rooms. I'm sorry. So yeah, I thought I would be able to muster up the incentive to do it, but I can't. So why don't you could chat with a friend if you want, or, try to make this as interactive as possible. You can harass Jay and say, hey, this is what I think. Is that true? Yeah, it just wastes a lot of time, the breakout. I mean, if we weren't doing physics, there'd be a time and a place for that if we were going to have long, flowery discussions. But I appreciate the comment. If you really like breakout rooms, you could send me emails too, but I don't know, for what we're doing, the amount of time to do it just seems to waste a lot of energy. All right. And so, and I appreciate you guys being brave and not worrying if you sound stupid. That's like the classic thing students worry about. You're like, do I sound stupid? Trust me, you do not sound stupid. This is a physics class. Nobody has a clue what you're talking about anyways. You'll sound like a genius if you speak up, even if you're wrong. So yeah, anyways. All right. So when is this thing speeding up? So let's think about this. Maybe and just do these first four. Don't worry about part E. So I'll give you a second to think about that, and then we'll regroup. And if you want, you could text someone in the class randomly, privately, if you want, or you could just think to yourself, whatever you want. So I'll give you about a minute and a half on here. So when my clock says 11:11. Oh, let's go 11:11 and 11 seconds. Nothing could be more perfect than that. It's even better than a Yahtzee. Man, I should have played the Jeopardy music. So I didn't really see who just came in, but what we're trying to do right now is we're trying to look at these first four questions that you could see on my screen. And at the magic time of 11:11 and 11 seconds, we're going to go over them. So you could text anybody you want, or, scream it out the window, whatever you feel is right to help you have fun with this. Hey, Jay, are you able to see the clock on my screen, on your screen?
Yes, we can.
Oh, okay, cool. Oh, there's the time. 11:11:11. All right. So if anybody's feeling brave, and I can't see any of your faces right now. So if you want to be anonymous, you're totally anonymous, and nobody on the live stream will see it either, I don't think. So when is the object speeding up, or is it? What do you think? Somebody give it a shot.
From 0 to about 1.9 seconds.
No, and that's a good thought. All right. So do you agree that there's velocity there? Absolutely. There's velocity right here, this orange line, right to there. And if you're colorblind, I apologize here, but there's velocity, but is the velocity changing? What do you think?
No, it's constant.
Yeah. And so then it's neither speeding up or slowing down. And actually, that's going to be something right here. Do you agree? That's one of the times it's traveling at constant speed. I guess since we jumped into part D there, what is the other time that it's traveling at constant speed?
2 to 3 seconds.
Right. And now this one's a little bit goofy. Somebody could say, well, it's not traveling at all. Yeah, that's semantics. Okay, I understand. But we do agree that it's constant speed from 2 to 3 seconds. Now, a common question that always comes up, there's always somebody in the class that's mathy and is like, oh, do I need to use 0 to 4 and use closed brackets or open brackets, or 0 to 2 or 1.9 or whatever, 1.95? To be honest, I don't care about those brackets at all. Okay. So if you want to use open brackets, closed brackets, if you don't know what I'm talking about, any brackets go tonight. I think that's an Axl Rose quote, but yeah. So, all right, that's good. I don't care about the brackets, whether you use open or closed in my class. All right, so let's let somebody else have a shot. So we know it's not speeding up from 0 to 1.95 seconds. So is it speeding up at all, ever?
After 3 seconds.
After 3, let's see what the chat says here. Okay, it is after 3 seconds. Now this is weird. Let me see if I can get my right there. It's speeding up. Now you might be saying the velocity is getting more negative. Yes, but the speed is the absolute value. Think about it like this. At this point right here, the speed is equal to 2 meters per second. The velocity is equal to -2 meters per second I hat. And you can see the joy of physics, and I'll try to catch up in the class. I don't know if that addressed one of those things. So that was, here's when it's speeding up. Oops, that was crappy. Let me just put the arrow there. So that was when it's speeding up. And I'm going to try and catch up with the chat real quick. All right, right on, Daniel. Sneaky, right? You could, yeah. So, okay, watch out for that one. And obviously, I guess I should be careful here. To be clear, up down here, V is now 4 meters per second. So you can see the speed is actually increasing as you go on. And down here at the bottom, V is equal to 6. So it is speeding up slowly. All right, that's cool. So when is it slowing down? Somebody else.
Right before the 2 seconds.
Yeah, right there. That's the slowdown, right? And so that's probably this time interval, right? Oh, wait, not that one. The one right after it. This one, 1.95 to 2 seconds. All right, that's cool. And then when is it at rest? Well, I think we kind of already discussed that. So I'll do this here. That's also the time it's at rest, right? So it's kind of debatable whether you should say it's traveling during that time, but that, yeah, the idea is it's a constant speed. It also happens to be at rest. So whatever. Yeah, that's good enough on that. All right. Any questions on those 4 parts before we go on?
Can you explain again why it's increasing from 3 to 6?
Yeah, yeah. So let me take a look here. The idea is this right here is not speed. That is velocity. And so on all of these numbers, the velocity here has an implied I hat, right? Because it's moving left and right, we assume there's an I hat on everything. Okay, it says it's moving in one dimension, and you're supposed to know this. That's something you're supposed to just know from that sheet of, from, I don't want to lose my drawings here, but basically from this thing, I don't know if you could see in my tiny window up there, that list on page 31. That's just a fact you're supposed to know. If that's true, then this is the velocity. The velocity is becoming more negative, right? More and more negative. -6 I hat here. I'm going to leave off the units and the letter, but it's getting more negative. However, speed is the magnitude of velocity. So the magnitude is getting bigger. It's getting more and more negative, which means it's becoming a more and more negative number. But then when you slap an absolute value on it, which gives you the speed, that number is actually getting bigger. Here's another way to look at it. Over here, do you agree the slope is negative?
The slope of the purple line?
Yeah, the pinkish whatever color, yeah.
Yeah.
And do you agree that implies the slope on a VT is acceleration? Acceleration is negative, but also velocity is negative. We see that same sign. And so whenever they have the same sign, speeding up.
Okay.
Is that helping a
Yeah.
little bit?
Yeah.
Here's another way to think about it. As crazy as this sounds, let me just give me a second here. That blue line, that light blue line that I just drew is the time axis. If you are on a VT plot now, a VT plot, everything that we're talking about here only applies to a VT plot. If you are on a VT plot and the line is going away from the time axis, you're speeding up. Because on the top, it makes sense, right? If you're going to a bigger number on the top, you're like, yeah, I'm speeding up. And then on the bottom, you're getting farther from 0. If you're getting farther from 0, your speed is increasing. Is that all helping out?
Yeah, and I get it now. So if we're looking at the time axis,
Mhm.
the further you go from it, the more you're speeding up.
As long as you are on what type of plot?
VT.
Mm-hmm. Perfect. And isn't that funny? That last way, for me, it's almost easier to think of it that way, right?
Right.
So, but I think it's good to know all of these ways, and I think they kind of tie together, and I think it makes that last way stick better. So, all right. Should I clear all these drawings now? Anybody have any other questions before I clear it all?
Mm.
You good? Okay.
Yeah, I'm good. Thank you.
Okay, cool. I'm clearing it. Let's do it. Remember, you can always go back and watch the live stream later. So now I think, let me zoom out just a little bit more. So now we're ready to tackle this part here. Determine the displacement on each interval. Before we do that, somebody remind me, how do you get displacement from this type of plot? Again, let's focus on what type of plot first. We have a T here and a V up there. We have a VT plot, right? So if we have a VT plot, how do you get displacement on a VT plot?
It's the area under the curve, right?
Area. And you could kind of see the areas popping out here, right? Where's my drawing tools? You could see we've got an area right here. You've got this little triangle that's kind of hard to draw. So maybe I'll shade that in a different color. We've got this area right here. And then finally, we got this other area way back here. Let's do a different color for it. How about this one? I probably should have kept the other color coding, right? But whatever. Let's go back and change that just because it's only two things. So we got this section right in here, and this is all orange. And then we've got this big pink section over here. That matches the color from the previous part of the video. So the idea is we need to get those areas, and I'll do one for you. I can tell the area right here is 0. Whoops, I did a different color there. I think okay, you get the idea. So go for it. I'm going to go ahead and stop the share, and I'll start working this out on the board too here. Okay. I'll just go to the whiteboard. So we had a plot here, look kind of like this. This was T. It was 1, 2, 3, 4, 5, 6 seconds, I think. Let me get this back up. About that. And then we saw right here, I'm exaggerating it just so I could see it. Something about like that. It's not perfect. That was 4. This is -6. And there's a few little tricks in here, so we probably better pay attention. All right. We were told that this region right here was 1.95 seconds. And so that means this little time right here was 0.05 seconds. And this was 3 seconds. This was 2 seconds. And I think this was, let's see, 1. Oh, shoot. Well, we'll cheat. There we go. That's easy enough. 1, 2, 3, 4, 5, 6. Perfect. Looks great. All right. And so the areas here, and this, I should be careful. This was time in seconds. This is velocity in meters per second. Always good to think about the units, right, Jay? I'm sure Jay does not like that comment. Yesterday, she just missed some points for getting the wrong units. Yes. And so what I did was I broke it up into a table. So that's a good question. All right. And so what I wanted to do, sorry, right there, I wanted you to get the area for each different chunk of time and then fill in this table. Remember, the areas are the deltas. And there's one little trick in there. So let's just go ahead and do it. I'll light up the whiteboard in a minute. And so the area here, this first area, that's pretty easy. That's just 4, right? But let's get the units. Okay, so if this is 1 second and this is 4 meters per second, it's 1 second times 4 meters per second. That area is just 4 meters. And so notice it has the right units. The next one would be, oh my gosh, this is going to take me forever. So I'm going to go ahead and, well, let's do a couple more. Let me get a calculator so I don't spend some time. The next one, the time interval is only 0.95 seconds, right? Okay, so the next one would be 0.95 seconds times 4 meters per second, which is, making sure I don't screw it up, 3.8 meters. And I'm getting lazy with sig figs here. You should keep 3, but I run out of room. This next one should be, it's a triangle, 1/2, 0.05 seconds times the height, which is 4. And so 0.5 times 0.05 times 4 is 0.1 meters. Another way you could have seen that is just be like, if I had gone all the way over there, shouldn't it be 4? Well, that means that little triangle piece, if it was rectangular, would be 0.2. So it should be half of that. Whatever. Hey, this one's 0. We got that one. Nice. And then from 3 to 4, we get a 1. Well, I guess that's 0.5 times, let's see, what's the time there? 1 second. And what's the height? -2. So that was one of the things I was trying to slow play it to see if you would forget the minus signs. You could use trapezoid rule or do anything you want. Yeah. The other thing, you could always split them into rectangles and do a rectangle plus a triangle. And that way might be nice because, this triangle you already computed in this step, right? So you could just be saying, add this rectangle to that triangle that I already did the math for, or whatever you got to do. You could also say, well, isn't a trapezoid exactly the same thing as a rectangle of half the height? And it is, because you say this little piece, if I take this little triangle right here and shove it right there, I get a rectangle. So there's all kinds of tricks you could do. Basically, with a trapezoid, it's just average height times the width. So if you want to do that, anything goes. I don't care how you get it done, just get it done. All right. Oh, I forgot to do this one. So 0.5, that's probably easy, isn't it? That's just 1. Is this -1? I hope so. All right. And so the next one should be 2 plus that. Shouldn't that be 3? And the next one should be 5, because each time you had a rectangle of height 2 and width 1. So yeah. And these, I screwed up. What did yeah. So what did I screw up here in these last 3?
The negative.
Negative. I'm such a bad person. Okay, there we go. All right. So great. What's the point of all this? Geez. So I just wanted you to remember a couple of things out of here. One, we did a velocity graph. Be careful that you use the velocity rules. I've stressed that many times on the quiz. When you screw it up, I'll probably just be like, well, okay. 2, pay attention to the units of a graph. 3, know the difference between slopes and areas and when you use them. For example, here, areas gets us position, distance, or displacement. What did the area get?
Position?
No.
Displacement.
Displacement. It relates to position. So the most common thing is people think, oh, when I integrate velocity, I get position. No. When you integrate velocity, you get change in position, which relates to position. Let's go see what these look like in the solutions, and I'll show you, okay? And so that's kind of the big ones right there. Slope would get you what? If I got the slope of that graph, what would we be getting? Why is it not doing anything? There it goes. If we got the slope of that graph, you would be finding the
Acceleration, right?
right. All right, so here it is. So there's kind of the plot. And so there's some different ways to see this thing. Now, we kind of worked all this stuff out, and you could see here's the acceleration. I don't know if I did all that on the previous page. Let me see. I forgot the question. Did I forget to do that? Oh, I forgot. Look, it said get the acceleration. So if you wanted to get the acceleration, you should get the slope. And so notice, I'll just stress a few little things about that. Here, do you agree that's a large negative slope? And this is a small negative slope. And right here, there's no slope and no slope. So we could see that no acceleration, no acceleration. That's the same thing as what you said for part D, right? And then let's go look at those numbers. How do you get the slope? Rise over run. So let's go look at that. Whoops, right there. Okay, and so you can see this equal sign that's kind of wavy I use to mean approximately. So it's debatable depending how you want to look at it, but yeah. And so notice here we get this large negative acceleration, and over this interval, the slope was constant and negative, so it's a small negative number. Okay. And then here kind of this stresses we were just talking about position versus displacement, right? Okay, and let me make this a little bit smaller. And so now I could see it both on the screen at the same time, I think. All right, the idea here, I want to point out a huge difference here. Oh, get this zoom crap. Okay, look at this. This is a delta x. It's a change in x. Down here, this is x. There's a big difference there. All right. And so notice, you might be wondering, why did this start at -4? Does anybody have an idea? I'll show you. You are told the object starts at -4. So that's what is the problem state. So notice there's a big difference between position and displacement. Right here, this tells me the initial position is 4 meters to the left. That means x initial is -4. We can't get that from the VT graph, but we do get it from the words of the problem statement. All right, let's go back and look at these plots. So that's why I started the initial thing at -4. Let's go back to the solution. This is actually a pretty juicy problem, right? You could see all the issues that come up in a physics problem in this problem. So I am told this number. Then I know from 0 to 1 seconds, I change by +4. That gives me this. Next, I know from 1 to 1.95, I change by about 4. And so notice I'm right there. And so these changes keep adding up. And you could keep going to different colors, but I'm going to run out. So right here, this tells you why I'm up up to 3.9. Then it doesn't move, and then it starts moving left. And so we end up in this weird fashion. Now, this is pretty tricky to run that simulation because it's hard to get a negative 80 acceleration. So what I did do is make the plots for you so you can kind of get another feeling for this, okay? So let me clear all these annotations. But I guess before I do that, is this kind of helping with the difference between delta x and x or not? I don't know if this is helping you. It's a lot to take in. All right, let's keep going and see. This is what the plots look like. This one was what we started with. This is what we were given. We were also told this piece of information right here, the initial position. Now, where is it? Oh, come on. We were told right here what the slope is. Isn't that the slope of the xt graph? So that's how you get the slope up here. This has a slope of 4 over 1 up 4 over 1 up 4. Notice the following. Students are not used to this. This is 1.5 here. I didn't label it, but a lot of you screwed that up last time. Remember, I'm only going to mark some of the increments, but show a lot of grid lines. So it's your job to know how to divide the grid lines out. But yeah, we see over 1 and over a half up 2 would be the same as over 1 up 4. All right, so that's that slope. Right here, this negative slope acts for such a short period of time, it doesn't do much there, right? You don't really see much happening. But we do see, and this looks like it's not exactly perfect. The computers do it a little bit of rounding there. That should be perfectly flat, right? So the computer kind of put in that curve there. And then for this last part, you can see it starts to take off downhill like that. So I need to go in and add some more points so that this doesn't do that weird numerical curving. But yeah, you get the idea here. So it's approximately right. That's, again, you can see here, there's a negative slope. Then there's a larger negative slope. And then an even larger negative slope. So that's how you go from the VT to the XT. You're looking at the slopes and you're looking at the changes. One more thing on this. This is so dense, isn't it? There's so much to learn here. It really takes a lot of practice. Yeah, of course, if you want to be a competent scientist of any kind, you have to know all this graphical literacy stuff. So this is probably more important than some of the other stuff. You really need to understand graphs inside and out, what the slopes and areas mean, all right? Let me clear this out. All right, so we use slopes to go up that way. Slopes, VT is slope of XT. And similarly, area of VT gives delta X. That's the summary of what I just said, right? This has an area of, we said, I think it was 7.8, that whole square. Well, notice you go from -4 all the way up to 3.8. That's a change of 7.8. Leaving off the units just to get it done. Next, let's go down here. Oops. Here's how you get from here to here. Now we could say, well, going from here to here, slope of VT gives A. So notice there's a subtle difference. In the last one, VT was the slope of X. In this one, slope of VT gives A, right? There's a subtle difference there. Here's that large negative. This goes all the way down to -80. And then we see there's no slope, a large negative slope, no slope, and then a slope of -2. All right. That's a lot of information. I should pause. Is this making any sense at all? Or we probably need to do a couple more, right?
Yeah, a couple more.
Yeah. Okay. And so probably what I'm going to do is we just did a VT graph, and whether you like it or not, I tend to like try to alternate between VT and XT to deliberately try and force you to be like, wait, am I looking at the right set of rules? So if you don't like that, you can always tune out and just start going through the book and grinding through problems. But at this point, we're kind of done. I'm going to do more and more examples, but we've covered all the new material before the quiz. So now it's just practice. Why don't we try the next problem? 2.28. I'll share it on the screen for a second, okay? I don't know. And yeah, were there any questions before I rush on? I feel like I'm going really fast. Just trying forcing myself to slow down. All right. Unmute. You could ask Jay if I'm too intimidating. I know sometimes I scare the hell out of people, but all right, not trying to. All right. So I'm going to look at this 228, and why don't I make it a little bigger? So, oops. See there. Yeah, I'm only like 3/4 as scary, right, Jay? All right. So here's a strange little tidbit. I wanted to name one of my daughters Zycra. Of course, I was vetoed by their mother because she thought that sounded like an antidepressant medicine. But I wanted to name my kids Vega and Zycra. I did not win. That said, we should probably do the problem. All right. So now we have, okay, you can see I'm doing it to you right now, position versus time. So again, always look at the axis, always look at the units. Think about that crap. Next. Zycra is moving right and left. Okay. So now on the XT, let's try this as a group. I'm going to put the timer up. Just try and get this one. So maybe parts A, C, and D. Oh, why not E too? So these ones I think are best done as a group, and you could chat with somebody or, text back and forth. Just pick a random name in there and say, hey, this is what I thought. What do you think? I'll put the timer up for a second. Okay. I'll give you a second. So try parts A, C, D, and E. We're on a position graph now. Can you do the same types of questions? When is it speeding up and slowing down? It's a lot harder. If you want, you could always private message me in the chat here. All right. I don't know. Does my chat show up on your screen, Jay?
Messaging done directly to you?
No, like right now, can you see the window that I'm moving around that says chat?
No.
Okay, that's what I thought. Just making sure. So yeah, if you want to private message me, it won't show up on the, I don't think it'll show up on anything. So yeah, if you want to discuss your answers with me, or you could discuss them with Jay. Discuss them with Jay. She's cooler than I am. All right.
Not kidding right now. I'm making my sister's birthday card because I'm just sitting here.
Okay, cool. That's all right. Do it. I'll give you another, well, let's go 11:44:44. That seems like a good time to start back up. So again, we're trying to answer those questions with the red arrows on it. Just giving you a second to think before I harass you and ask you guys to speak up. And you don't need to look in the solutions, but if you already did, okay, that's cool. I'll try not to for this. Oh my gosh, we made it. Okay, so I have no idea if I'm giving you the right amount of time, too little, too much. My bad if I screwed it up. But let's go ahead and somebody feeling spicy. When is this Zycra alien moving to the right? When is Zycra moving to the right? Take a guess. It's okay to be wrong.
Can I give it a try?
Yeah, go for it.
Okay, I think that Zycra is moving to the right from 0 to 2 and from
Okay.
4 to 6.
Okay, 0 to 2, and you said 4 to 6?
Yes.
So let's see. In this case, so 0 to 2. And what makes you think it's, and you said 4 to 6?
Yes.
Okay. And now what makes you think that? What's going through your brain, just so I can try to understand?
Because the problem says that going to the right is positive and concave up, which is what the graph is doing, means that the acceleration is going to be positive.
Okay. So let's pause right there. Concave up. You said that correct? And that you said that acceleration is positive. Now watch out. Moving does not mean acceleration. I want you to associate the word moving with velocity.
Okay.
And so give yourself a second. Everybody, that might affect you. So he is correct about these two facts. He is absolutely right. And I'll throw in the concave down in the middle for you. Do you agree that that's true, everybody? I hope you do. So he's absolutely right about these 2 times having positive acceleration, but he is wrong about the thing being moving to the right then. So give it another shot. Give yourself a second while I'm writing here to think.
You said associate like movement with velocity.
With velocity. So how do you get velocity from this graph? Does anybody know? Help him out. You don't have to do it. Somebody else. Tell us how you get velocity from this graph.
It's position over time.
Okay, which is, what's another name for it?
Derivative.
Derivative. What's another name for derivative on a graph?
Slope.
Slope or tangent line. Yeah. So we need velocity is the slope. So tell me, from right here to right here, on average, what do you notice about the slope?
It's downward, negative.
Slope is less than 0. So what does that tell us about the velocity?
That it's moving to the left.
Yeah, or it's less than 0. So
Right.
it's left, moving left. So let's use that. So everybody kind of use that reasoning to think it through now. Okay, so it takes me a long time to write on the screen here. But so basically, right from 0 till almost 1 second, it's got a negative slope. Now that slope is changing. And in fact, you can see that the slope is getting smaller and smaller. It's going from a large negative number to almost 0, but it's still negative for that whole period. So somebody else, what's the next interval here that I should worry about for the velocity?
1 to 2.
1 to 2. Do you agree I could also go all the way up to 3?
Yeah.
And so here, slope positive, which says V is positive, right? which says moving which way?
To the right.
Moving right. So far, so good. And so we see all of this part right here. You're moving to the right. Are there any other time intervals you're moving to the right?
Yes.
5 seconds enough.
5 to 6. Yep. And so the dashed lines there, so that would be this answer. From what is it? And this is what I was saying. Who cares about those time intervals? What did we say? From 1 to 3 and 5 to 6. That's not good enough. What did I forget? This would
Units.
not get, yeah, exactly. Now in Canvas, you're not supposed to enter units, but on the final exam, oh man, if you leave off units, I'm going to tear you guys up. All right. So yeah, just, oh, that looks like a 5, doesn't it? Let's try and make that look more like an S, a beautiful flowing S. Oh geez, I give up. All right. So yeah, that's the times. Make sure you include units on these questions. Every year I tell people that. Every year people lose a lot of easy points and lose a letter grade for it. So yeah, it costs you eventually. All right. How do we get estimate? So I think this question now probably makes a lot of sense. How do you estimate the velocity at t equals 4 seconds? Is it 0 or is it non-zero? What do you think?
Non-zero.
Non-zero. So how do you do that? Slope. Now, the most common thing students screw up, I've seen this many times. I was shocked when I saw this at first, and then I realized that's just the way students think. A lot of people would go from this point down to this point and get rise over run. That's approximately right, but do you see how it's not really that close? That's terrible. And I'm like, okay, you just lost points. So that's a bad idea. You should go from, say, this point to this point. Sure, it's a little more work, but isn't that almost perfect? So what I have learned is to remind students, be sure when you're taking the slope, pick a point in time just before or just after, and ideally just before and just after, and compare them. Sometimes you can't do that, but like, just think, if you compare this point to that point, you'd be good, or this point to that point, you'd be good. So try and pick points close to the time of interest. And that answers in the solutions, but you could get rise over run from that and estimate it. Typically on these types of problems in Canvas, I jack up the error tolerance. So instead of having only 1% or a 0.5% error tolerance, I'll give you something like 10% or even 15%, because reading a graph is a little harder. All right. So expect that in Canvas, when you have to do this, you're going to get a larger error tolerance. All right. That said, let's clear all that out. So we've kind of done this one and this one. I gave you some time to think about these. Let's see how you did on them. When is Zycra moving left and slowing down? Okay, moving left. Remind me, moving left, what do I want you to think? Do I want you to think about A or V?
V.
V. Do I want you to think positive or negative?
Negative.
Negative because of left. Slowing down. What does that mean?
Approaching 0.
Okay, that's difficult on this plot though. What's another way?
Acceleration is greater than 0.
Yeah, or acceleration is opposite sign. That's really what goes in my mind. And then he went the next step, whoever that was, to say, in this case, sorry, I'm so slow. Let me get this out of here so I have room. I think he said A was greater than 0, right?
Yeah.
So what does that mean? We need a region with, what does V equal, V less than 0 means negative slope, right? On the XT plot, that's what it means. And then A equals 0, what does that mean? Somebody said it earlier, or A greater than 0, that's concave up. On the XT plot, not on the VT. right? Okay, so in this case, we need to find a spot with a negative slope and concave up. So here's the concave up. Let's get the concave up marked. Sorry if I'm not that fast. There's concave up, and now we also need negative slope, right? Well, isn't that right here? And then not right there, and then right there. Those are the only regions that have both of it. I guess this is also a negative slope, isn't it? But that's not in our concave up region. I think that's it. So we see that these time intervals here, 0 to 1 and 4 to 5, meet the requirements of what was asked. And then I would say 0 to 1 seconds. And 4 to 5 seconds. Is that making any sense at all?
Yeah.
Yeah. So you could see I'm going to have to clear my drawings pretty soon because it's getting out of control. So I thought I'd pause and see if anybody has any more questions about this while all these sketches and colors and stuff are up here. And you could tell this is tough on students that are colorblind. I have had them occasionally, and it's just really a hard part. So if there's anything, if you're colorblind or something, just give out a shout. All right, and let me know, and I'll try and say it a different way. All right. Okay, moving right and speeding up. Whoops, still on yellow there. Let's clear all this out. If we're doing moving right and speeding up, moving right says what? Positive slope, right? So I'm skipping a step. Positive slope. Why am I saying positive slope? Because that means V is greater than 0. Speeding up, in this case, speeding up means A, same sign, which means A is greater than 0, which means concave up. So I think you can go out in the region and find those. Let's see. So I need a positive slope and concave up. That's right there. Also right there. I think that's it. And I think this last one is actually pretty easy. Time interval when, let's do that in a different color. How about purple? E would be this time interval right here, right? Concave down. All right. That's a lot of information, right? I'm going to clear this out. Stop the share for a sec. It's intense. Remember, you could ask Jay anything you want there, because if I'm going too fast and you're scared to slow me down, I'd rather have you slow me down and ask questions, but I have no idea how this is treating you guys at all on Zoom. Normally I walk around the room and can see. So it's really hard to teach this way, but I don't know. What do you think? Any feedback at all? Is this getting better? It probably isn't getting that much better yet, to be honest, because we did a VT and an XT. The second time you do a VT and an XT, it should feel a little better, right? But those first ones probably felt totally different because they are. All right. Strategies for success. Identify the type of plot, get the right set of rules, think carefully about units. Always remember to know the difference between what a slope versus an area means on the plot that you're working with. Okay. What does the slope mean? And then when you write your final answers, check the units again. All right. That's kind of the summary of that. Jay, can you? All right, thanks. So I'm going to show you a couple of problems here. I'm going to tell you some really good problems here. So these are some good problems you might want to do at home. Let me just do it on the whiteboard. That way, if it doesn't show up in the live stream or so it will show up in the live stream. So generally speaking, as you go up in problem numbers, the difficulty increases. So, but I think you could probably do the previous ones again without looking at the solutions and see if you actually understand them. So I swear, I think doing 2.27 through 2.29, and I don't think we've done 2.29 yet without the solutions again. Make sure you could do those ones without the solutions and haven't forgotten what we just did. Oh yeah. Boy, I tell you, every problem is good in here. The 2.29 and the fractions, I'll say P over Q, where P and Q are rational numbers. We're going to do one of those next. I'll show you what I mean. I should just not lie to you. Just do every problem. You aren't going to get this unless you do every variation here, but 230, I'll put the most important ones. I think they're all important because I truly believe understanding graphs is critical to your ability to succeed in anything. So I don't know, right? I guess 31 and 32 aren't as crucial. Let's see. 33 and 34 are big time, okay? This is almost like you should save these ones for last and try to do these without the solutions and see. I put every single possible scenario I could ever imagine putting on a test into these two problems as far as XT and VT. One of them is an XT and one of them is a VT. And the idea is I did everything where it was sloped up, sloped down, flat, curvy, whatever. And it's all in these two massive problems. And so if you really want to see if you know everything, this gives you every possible case that could show up on a test question relating to an XT or a VT graph. So try to save these for last, try to do them without the solutions, and then check it as if it's like a quiz, okay? And then go back and fix up everything, read the solutions. They're pretty detailed. Yeah. All right. So, yep, you really learn it from that. So now I want to try one of these weird 2.29 and a fraction. I snuck in a couple extra problems on you. Oh, well, there's only 38 plus 10 of these or whatever it is. Let's take a look at one of these together. And I think they're kind of fun. They're very conceptual. So this would be a good time to practice these. So let's go take a look. I have a strange definition of fun if you haven't figured that out. All right. Let's see. Did we just do a VT plot? I think we just did an XT, right? Let's try it. Let's just do this one. 2.29 and a quarter. Okay. So here we have 4 objects. 1, 2, 3, 4. And at any time now, at this point, you know everything I have to say. So if you think you don't need to listen to me, it doesn't offend me if you leave, okay? So if you want to take off and work on problems, just make sure you do some physics problems for the next 20 minutes if you're at home doing whatever, okay? Give you 20 more minutes of hard work on this at least. That said, if you want to stick around, let's keep working together and look at this one. The graphs of velocity versus time are shown for objects moving. Okay, VT. I'm going to circle that before I forget. I want to remember I'm looking at a VT plot. I'm not doing XT anymore. Okay. Let's see. Who's feeling frisky? I tell you what. I'll give you a minute to kind of read through these, and then I'm going to start picking on you guys, okay? Well, let's just go to say 1205, okay? Yeah. You can send a chat to me or to Jay if you have a question really quick or whatever. Okay, so that's 1205. Do you guys like that when I give you a second to kind of read without me, or is that wasting your time? Because I did that 3 times today. Is that a good thing or a bad thing?
I like it. I think it's cool.
Just gives you a second to kind of, before I
Yeah.
harass you and ask you questions.
I know like what you're talking about a little bit more because I had a little bit of time to read.
I gotcha. Okay, right on. If that starts to annoy you, just let me know. Or if I'm bad at it, tell me like, could you do this and that? And I'll just try and read. And I'll shoot for the middle of whatever people tell me, right? So you never make everybody happy as a teacher. Rarely make anyone happy, actually. All right. So that said, all right, let's take a look here at this this question right here. Do you guys see any objects that have constant acceleration in this case?
Object 1 and 2.
Let me see. 1, that would be this dotted line here. And 2, that would be this one. And what makes you say that?
Because the slope would become the acceleration, right?
Outstanding.
So if the slope of these is a constant slope, that means the acceleration should be constant as well.
Right. Would that also be true if we had an XT graph? Would it be constant slope? Would constant slope indicate constant acceleration on an XT graph? What do you think?
It'd be 0, right? So technically constant.
Yeah, good. That was a really sneaky one, wasn't it? All right, that was pretty cool, dude. All right. Okay, next. So that was that one. Great job. Sneaky, right? A linear XT means A equals 0. 0 is a constant. All right, that was sneaky. Okay, so how about this one? Which object or objects have positive acceleration? Now, to be clear, the acceleration could be changing, but it should always be positive. Do you see any of those? What do you think? Anybody?
Give me a second.
Okay, I'll give you a second.
Nope.
What does positive acceleration mean on a VT?
It'd be the positive slope, right?
Okay, do any of these have positive slope?
It'd be objects 1 and 3.
1 and yes, this is a positive slope. It's getting bigger, but it's still positive at all times. So I agree, 1 and 3. Nice. Okay, so there's those two. And you could argue, wait, what about at 0? Whatever. I think I answered that in the solution of like, you're right, it's debatable. So hopefully I try not to give questions on a quiz that are that ambiguous. Or you could write some words in a normal final exam. All right, so we finished these two. Next, at what time or over what time interval is object 4 at rest? Okay, so object 4 is, let's see, the big dashed, this one.
Would it be from 1 to 1.5?
Nope. That's a good guess. Not quite. Anybody else? What does it mean to be at rest on a VT plot? What does it mean to be at rest? If you're at rest, what does that mean?
When it crosses 0.
Yeah. Okay. When what crosses 0?
The function
What are we plotting here? What's the function?
Yeah.
velocity.
Velocity. Yeah. So do you agree at rest that implies v equals 0? Now, on an xt plot, that means the slope is 0. But on this plot, well, we're just looking at the frickin' numbers. Isn't it equal to 0 right at that time? Oh, maybe that's what you meant, between 1 and 1.5, like at some point in time. I see. Is that what you meant? I didn't understand you earlier. But yeah, I'd say like at 1.4 seconds or something. And maybe that's what you meant, whoever that was earlier. And you might say 1.35 or whatever. I don't know, whatever. That was good. Any questions about part C? I'll stop talking for a sec. Okay, good job. And so if I didn't understand you when we were first talking, my apologies. We got these ones now. Okay, when is object 4 speeding up?
After 1.4.
Pretty good, right? There, the speed is getting bigger. The velocity is becoming more negative. Here, the speed is going down from 0 to 1.4. But from about 1.4 past that, we see it speeding up. Outstanding. Or you could say it's getting away from the time axis. Okay. All right. This is always a fun question. Students hate these. Rank. Rank the speeds of the object at time equals 2 seconds. So, okay, that's at the end from largest to smallest. Which one has the largest speed in your opinion here?
Object 3.
Let's see. Object 3. So
Wait,
what
never mind. It's gonna be object number 1.
Okay.
That's where it speeds at velocity, right?
Okay, so he's saying object 1.
It's the highest.
Anybody? Okay, so that's pretty good. Anybody else have an opinion? Is he
Wouldn't
right?
object 1 and 2 be tied for first?
I don't know. What do you think? Speed is the absolute value, and so they're both about 6. So I agree. I would say V2 is equal to V1 if we're talking about speeds, right? Was that Dom earlier? What do you think, Dom?
Yeah. Oh no, yeah, I agree. I was
Okay.
acceleration for a second, but
And then I see what you're doing. You were doing the, yeah. So he was saying object 3 had the greatest acceleration. I agree with that, right? It's the most slopey right there. So nice job. Okay. And then probably the other two are tied as well. What do you think? This is what, 3 and 4?
yeah.
I'd say 3 and 4 are about tied too. So as far as speeds go, what do you think? Should we do another one and call it a day?
Yeah. Yeah.
With an XT plot this time?
Yep.
And so I think these ones are pretty. And so I do think that I made these up so that you guys could have some time to maybe play around with these. So let's maybe go on to 2.29 and 3/4. Okay, is that an XT? Yeah. And so then there's 2 more for you to do outside of class, which I'll probably do in the other live stream or something. Are there 2 of these or 5 of these? I don't know how many I got. I think I have 2 XT and 3 VT. So yeah, let's do an XT. All right. I'll give you a minute and then we'll look at it. Ooh, A through J. Yowza. I missed 12, 12, 12. I'm such a bad person. Let's try 12, 14, 16. That's a pretty good time. Oh, I missed my time. Okay, that's close enough. All right. So let's see if I can see some people here. What do you think? So maybe somebody wants to chime in that hasn't been speaking up. If you want to, that's cool. If you don't want to, that doesn't bother me. But yeah, what do you think? Anybody want to try part A? We want to rank the initial speeds, and we're on an XT plot. Just kind of talk me through it, what's in your brain, or just say the answer, whatever you think. So we're looking at this one.
Would they all be the same?
And let's see. So what makes you think they're all the same? Kind of walk me through it so I can understand.
Because this is a distance versus time graph, right?
Nope. It's a position. You're
Or
close.
position, sorry.
Which do you agree that's very similar, but not quite the
Yeah.
same? Because distance would always be positive, right?
Mhm.
Position. So distance versus time would probably be the absolute value of this plot. So anything below the time axis would get flipped up, and that'd be really complicated. Okay, position versus time. But yeah, I got the idea. I know what you meant. Okay, so you said position versus time. How do you get speed from that?
So I was just thinking of just whatever is at 0. So since it's all position, it just means that they're all just starting at different places, but they all have the same speed, right?
Okay, so you're saying, if I understood you right, you're saying that this value is x initial, right? So they all start at different x initials. Is that what you were implying?
Yeah.
I agree. So there'd be x initial 1, 2, 3, 4. I'm going to screw up the labels because I'm having trouble writing right now. But yeah, okay. But how do you get speed from an XT plot? What's the general strategy? Or is it area? Is it slope? Is it what?
Slope.
Almost.
Oh.
What is the slope of an XT plot?
Velocity.
Yeah. How do you get speed?
Absolute value.
It's the absolute value of the slope. Isn't that sneaky? Yeah. So watch out. The initial speeds means which one has the largest initial slope magnitude, or the largest absolute value of the slope. Sneaky, right? All right. So let's see. Do they all have the same slope initially? This one is initially almost 0. This one is initially almost 0, right? This one's like slightly up and this one's slightly down, but yeah. So those two are close to 0. This one's kind of medium slope, and this one I would say is even steeper. So I would say this dotted line, so I would say 8. Oh, 8 is the largest, excuse me. Just a second. So the question asked for us to do, to be honest, I don't usually care too much if you rank them smallest to largest on a paper and pencil test, but boy, you better get that right on a Canvas test, right? So in this case, the smallest is probably, let's see, this one and this one, which is what, 7 and 6. So 7 and 6 are about the same. Next, it's the solid line, which was 5. And then finally, that's less than 8. Did that make any sense at all? Is that helping?
Yeah.
Can I-
I just had a quick question.
Yeah.
Like Canvas test for this kind of thing. Would we just be able to put like the 7 and 6 like interchangeably? Like
It would probably be a multiple choice.
it
And so you just, or a drop down where you just select a drop down or something.
okay.
Yeah,
Alright.
that would reduce that type of issue.
Okay.
And a lot of times, I don't know how to do ranking questions in there. I do think they're good to practice because it forces you to think about a lot of cases. So you should definitely do these ranking questions. But I think for right now, it's all going to be like, I would ask which one's the biggest. And then the next question would be which one's the smallest. And then one of the answers might be they're all tied, or 5 and 6 are tied, or 5 and 7 are tied, or 5, 6, 7, and 8 are, yeah. All right.
Okay.
Okay. Now, what's the difference in part B? In part B, we're supposed to go from least negative to most negative. And we're talking about velocities. Oh, man. And we're looking final. What time is that? Out here. We're looking at the slopes at these times. And I'm just starting to pick up the pace because I see we're running out of time. So you would look at those and say, well, this one has a large negative slope. So that's probably the last one. Small negative slope, small positive slope, large positive slope. So I would say 6, and then 5, and then 7, and then 8 for that next question, something like that. And these are all worked out. I do think, if you do all these concept questions and just check them, don't overthink it. Do one, try not to look at the answers, and then check the answers. And when you screw it up, go back and learn why. Then do the next one. And if you do all of these, your conceptual knowledge of these graphing questions will be through the roof, and you will be pretty good. And that should help you with the numerical questions, right? What good does it do you to go out and do a slope or an area if you don't apply it correctly? So the purpose of these 29 and fraction problems is to just make sure you know what the right rule is. And instead of doing the math, just kind of look at it and get a feeling. Don't waste a lot of time, trying to get the exact numbers and saying, just kind of look at it. And in the solutions, I do that too. I'm like, I can't kind of tell. So here I thought it was this, maybe you thought it was that. So the answers, I try and think just like you would. Okay. So yeah, I think that's pretty good for class today, probably. Did a lot of screen share today. I don't know, but with the graphs, it takes so long to draw them on the board. That's what I figured was probably best. So won't always be doing so much screen share and writing with that.